So dots versus lines, either one works. It's hard with the CLs if you can't keep like that in your mind, then it is difficult. All right, so draw a little structure for NH3. Who's going in the center for NH3?
Nitrogen.
Nitrogen. What did you base that on?
Because hydrogen has 3 next to it, and it's only nitrogen is the only unique one.
That is a great way to do it. Nitrogen is the only unique one. You could have also said that hydrogen can only get one bond. So if we put hydrogen in the middle, we're kind of done, right? That would have worked as well. But uniqueness is definitely something. The world tends to go with symmetry. I mean, look, we have bilateral symmetry, right? So I'm going to go ahead and start with this being symmetrical. This is not the actual shape that this would look like, but on paper, it's decent enough. We know that we have a total of 8 electrons available. Again, those electrons are found by looking at the group number for each of these. So 5 plus 3 is 8, 2, 4, 6, 8. It was mentioned to me like each of these bonds is 2 electrons, right? And a lone pair is 2 electrons. If you are having trouble with that, then you may want to read, start reading here where it says B. Either a straight line or a pair of dots can be used to represent a pair of electrons. If it's shared between 2 atoms, it's called a bond. An unshared pair is also called a lone pair or non-bonding pair. Now, our goal Monday of next week is to be able to make these. And we're going to need, actually it'd be Tuesday of next week. We're gonna need to make these at home. So I think the best way for you guys to make these at home, if you can, if you have somebody that's going to the grocery store anytime soon or something like that, tell them that, and if you don't, I mean, you can get this from Amazon or something like that, or you could just wad up paper. But the best way that you're going to be able to do this at home cheaply and effectively, other than wadding up paper, is to buy, they're called dots. So for your chemistry class, tell your parents that materials you need are called dots. And basically they're these little these little gummy guys, and they're kind of shaped like that. I don't know if you've ever seen them. I can bring up a picture or whatnot at the end if you don't know what these are. And you'll want toothpicks. The toothpicks are going to act like our bonds or our unshared pairs, and the dots are going to act like our atoms. You could use marshmallows, but you have to let the marshmallows sit out so that they get hard. Otherwise, it'd just be like, if you want to get fancy, tell them you need dots and sour gummy guys, because the sour gummy guys will be a little smaller than the dots, so you can actually have representation of the elemental size or the atomic size, right? So please get dots and toothpicks for next Tuesday. The quicker you get this, the better off you're going to be. So if we look at this CCl4, on paper, it kind of looks like this. We're not able to see the actual angles of it, right? Because it's flat. But if we look, it's actually 3-dimensionally what we call a tetrahedral. Anybody ever watch like the James Bond movie? And he's like getting followed, and he's like, we're gonna pop their tires. And he like presses a button and it shoots out all of these things on the back. Those things are in the tetrahedral shape. Because the cool thing about the tetrahedral shape is every time it lands, it's always going to still be having one up top like that. All of these angles are 109.5. So it always looks the same, no matter what. Anybody know the term for those things that pop tires, or they used when the cavalry would come in, when you would you'd have a rush of the cavalrymen? Starts with a C. Nah, caltrops. So CCl4 is a tetrahedral. Now we call this tetrahedral in electron arrangement and tetrahedral in shape. So that's electron arrangement and tetrahedral in shape. The bond angle for that is 109.5. 109.5, 109.5, 109.5, 109.5. If we look at NH3, we still have a tetrahedral electron arrangement. This right here is representing that lone pair. Now, instead of being extended out there, that lone pair is going to be closer to that the nucleus of that nitrogen atom. But it's still electron arrangement-wise tetrahedral. Tetrahedral. The shape of this, however, what's that look like? Right? Look at my fingers. What shape am I making there?
A triangle.
Triangle, trigonal. And if we look at it this way, instead of being flat, it looks like a pyramid. So the shape for that is trigonal pyramidal. The angles for each of these, because this bonding pair is closer, because this lone pair is closer to this atom, it's going to actually push these down. It's going to force these closer together because of that electron repulsion. So the angle for that is, instead of being 109.5, it's going to be slightly smaller at 107. Very cool. Now, if you have this printed out, you can look at the back. You can see the electron domains is the same as, I'm going to push this down a little bit that way. That's the same as the electron arrangement that I was talking about. And there are several tetrahedral arrangements. There's the tetrahedral one that we said looks like this, and it has a 109.5 angle. If we pull off one of the atoms it's bonded to, that makes trigonal pyramidal, which is 107. If we pull off another one and replace it with a lone pair, that's called angular, or sometimes you'll hear me call that bent. And again, we're going to cross out that 109.5 because those two lone pairs do force those together even more than 107 at 104.5. Now, to determine these shapes, it's kind of easy. You look at how many bonded atoms there are on the central atom. Well, there's 2 bonded atoms to the central atom. You check the number of lone pairs. Well, we said there's 2 lone pairs. So 2 bonded atoms and 2 lone pairs. That adds up to 4, which means it's tetrahedral in arrangement. But the actual shape only refers to the shape of the atoms themselves, not the lone pairs. So we can see how that would be considered angular or bent. And the angle for that would be 104.5. If we add another one on there, again, we now have 3 bonded atoms and 1 lone pair on top. So 3 plus 1 is 4, so that's still tetrahedral. But the shape of just the atoms is in a triangle shape, so trigonal, and it is not flat, it is pyramidal. At CCl4, we have 4 bonded atoms and 0 unshared pairs. That is 4 plus 0 is tetrahedral arrangement. And the shape of that is a tetrahedral as well. The angle for a tetrahedral is 109.5. So the reason for identifying the shape of these things is because on the paper they look flat. So we don't get any good idea of what they look like coming out of the paper or into the paper. So the other part that you were asked to do was to do these guys right here. So if we take a look, SCl2, S is in the center. CL, CL, keeping our symmetry. 6 plus 14 equals 20. Here's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Can anybody tell me the shape of that? Let's play the game. How many bonded atoms are there to the S?
2.
How many unshared pairs does the S have?
2.
2, very good. So 2 and 2 is 4. So the electron arrangement is tetrahedral. But what is the shape?
Angular?
Very good, Braylon. It is angular. Angular or bent. Now, does this look angular or bent to you? Looks pretty straight, doesn't it? That's because when we're looking at it, and when I drew that, I drew it like as if you were looking at it like this. You cannot see that angle. So you have to realize that even though something looks straight on paper, it depends on what perspective we have of it, right? A better way to draw that, if you knew it was going to be angular, just to represent it to somebody, would be like this right here. SiCl4. Si is in the center because it is unique. Cl's all around it. 6 plus, what we got? Not 6. 4 plus 28 is 32. Somebody want to give me a shape? Four bonded atoms, 0 unshared pairs, even though it looks like it for some reason. Louder?
Tetrahedral.
Very good. Oh, that's the I of the SI. This is tetrahedral. Good. CBr2Cl2. Now, let me ask you this. I said something about symmetry. So does it matter how I arrange these BRs and these CLs around this? BR is huge compared to CL, but if we take a look here, I've kind of drawn it like this, right? I have the BRs here and here, and the CLs here and here. If I take this three-dimensionally, I could put it like this as well, and I could have the CLs on each side and the BRs on top and bottom. Or I could have the BR on top and bottom, I'm sorry, the BRs on each side and the CLs on top and bottom. It doesn't matter how we do this because the actual structure is three-dimensional. What is the shape of this three-dimensional structure? You did. Oh, are you guys typing? You know I'm bad at the typing part.
Is it
Oh, yeah.
tetrahedral?
It is tetrahedral. Very good. Good. 4 bonds, 0 unshared pairs. Let's try this last one. In BR3. Two, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. 21 plus 5 is 26. Sorry, I'm at 24, 26. 3 bonds, 1 unshared pair.
That's the triagonal pyramidal.
Very good. Trigonal pyramidal. Very good. I think we just took one day off of the lesson this week, because that is kind of easy. The thing is again, we would normally have you memorize these. But any quizzes and tests you are taking at home, so you know that I cannot prevent you from using these. Wouldn't that be a sucker if the final exam all of a sudden, everybody's back at school and you don't have those memorized? It's gonna cost you then, right? Every time you have to look at something too, it does cost you time. All right, moving forward. Double bonds and triple bonds. Here's the key. What happens when the number of electrons that you added up is not the same whenever you're all done? Well, if everything must still fulfill the octet rule and you are short electrons, a double bond can be formed where two pairs of electrons are between two atoms. And by sharing two pairs of electrons, if you are two electrons down, by taking and sharing two more electrons with a double bond, that takes care of the loss. If you are, let's say, 4 electrons down, if your actual diagram has 4 electrons too many, then you would have to add 2 more bonds. Well, you could add 2 bonds in one way. You could make 2 double bonds, or you could make 1 triple bond. If you were 6 electrons down, you would have to add 3 more bonds. And keep in mind, there is no quadruple bond. Triple bond as high as it goes. So if you had to add 3 more bonds, it would have to be a combination of 3 double bonds or 1 triple bond and 1 double bond. So let's show you what this means here. Let's do O2. O2. So there is no central atom. If we draw this using the techniques that we have, 2, 4, 6, 8, 10, 12, 14. 14 is how many electrons I'm showing here. But when we add 6 times 2, we get 12. So I am showing 2 more electrons than I have available. That means I need to make a double bond, because I cannot show 14 electrons here if I only have 12 to work with. So I make a double bond. And when I do that, I have to remove electrons, because if I make a double bond, then I've gone from 14 to 16. That's taken me away from where I want to be. By making that double bond, I can remove now a line from here and a line from here, because that double bond allows both of these to fulfill the octet rule without 2 extra electrons. So notice I remove a lone pair from each to form that double bond. That gives me my 12, 2, 4, 6, 8, 10, 12, right? Looks kind of like E.T. If you've ever seen that movie. Elliot. Let's try it again. In 2, that's how we'll start that. I know I only have 10 bonds to work with. So 2, 4, 6, 8, 10, 12, 14. I'm 4 over. That means I need to make 2 more bonds. The only way I can make more bonds here is by making a triple bond. So that right there takes care of 2 of them. But if I look, 2, 4, 6, 8, 10, 12, I'm still 2 more over. So I need to make another bond. This triple bond is why most of the gas in the atmosphere is nitrogen, because it's very well held together. Triple bond is very difficult to break. Oxygen makes up 22% of the atmosphere. It's held together pretty well too. Luckily for us, it can bond to our hemoglobin and our red blood cells, right? Any idea why when I made this, I took away the top and bottom here and here? In reality, I don't like the way this one's drawn or this one. I would actually draw it this way. Any idea why? What are the lines?
Symmetrical.
Symmetrical, very good. This is kind of symmetrical too. I would say that that is definitely better. That is very good guess. Symmetrical. What are the lines representing?
2 electrons.
Electrons, good. And electrons have what charge?
A negative.
Yep. So why might I want to put them as far away from each other as I possibly can? Because negatives are going to do what to other negatives?
Like repel.
They're going to repel them, right? That's just a taste thing. I mean, it's good if you can get to that point. Obviously, I will accept this. Now, if you were wondering how we were going to show this with our dots and our whatchamacallits, well, you would just basically put 2 toothpicks through there. Now, in reality, a double bond, it has electrons basically being shared between here. That's the sigma bond. That's one of these bonds is called a sigma bond. Now, the other electrons here, these are called pi bonds. A double bond is made from one sigma bond and one pi bond. It's almost like if you shake somebody's hand and then reach around the side and pat them on the shoulder. The sigma bond is basically directly there. It would be made from s orbitals if possible. And the pi bond would be made from like p orbitals. Basically, you have sharing on one side and the other side, so it makes this connection. Now, if we were to look at N, we have a sigma and we have 2 pi bonds. So here we would have a sigma bond and then a pi bond and another pi bond that basically goes around the other side. And there you would have a nitrogen. What shape is this? Look at it like this, right?
Is it the triagonal planar?
Nope, not trigonal planar. Remember, all you're looking at when you tell shape is you look at the bonds. Very good. You counted up these bonds, and you said that each of these have 3 bonds. But that's not the case when you just have 2 atoms, right? Let's ignore the bonds for a second and just look at the atoms. What is that shape?
It's linear.
Very good. That's linear. So if you have 2 atoms, that's going to be linear. There's not much homework tonight, so take a quick second and see if you can draw the CO2. If you have scrap paper or whatever, see if you can draw the CO2 there. There's 2 choices you could make, and I think it's worth it trying this out. Is that enough time? Who has something like this? This is one option for sure, right? We have a triple bond between one of the oxygens and a single bond between the other oxygen. How likely do you think that is? What would be a better option? How about this? If we do this, we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. We only have the ability to show 12 plus 4. So that is 16. That means we're 4 over. So the option could be to sit here and make one side a triple bond. That goes against our symmetry. We probably should make each side get a double bond. What could we do to make this look better?
Have it like angular.
Very good. We angle them out, right? Now it kind of looks like an ET with a nose or something. What would the shape be?
Trigonal planar.
No. It's a trick again. Notice.
Would it be linear?
Yeah, right? Notice the shape here. It looks like a straight line, right? So the rigidness of these double bonds basically makes sure that that is straight. All right, so there are double and triple bonds. Remember, you only use those whenever your actual diagram is showing more electrons than you have available. If there is a unique atom conflict, I like to call this honk. And basically, hydrogens and halogens usually like to make one. Fluorine is a halogen. And most of the time, if a halogen is unique, it goes in the center and makes all at once, except for fluorine. Oxygen likes to make 2 bonds. Nitrogen likes to make 3 bonds, and carbon likes to make 4 bonds. Now, that is just what they like to do. That doesn't mean every nitrogen you ever see is going to make 3 bonds, but it's more likely to make 3 bonds than not, right? So honk, H-O-N-C, 1, 2, 3, 4. Whichever one can make the most bonds is the one you want in the center, because then you can have more branches. So if we have H2Cl, C is going to go in the center. If we want to make this symmetrical, I need to put the H's on top and the O on the bottom. We do everything else the same. 2 plus 4 plus 6 is 12 electrons available. 2, 4, 6. I only have 6 left. So 2, 4, 6. This carbon needs a lone pair. This oxygen needs 3 lone pairs. We count it up. 1, 2, 3, 4, 5, 6, 7. That's 14 electrons total. That means I'm 2 electrons over. So I need to make a double bond. Who here can make a double bond?
Oxygen.
You got it, oxygen and carbon. So we put another line there. We take away 1 lone pair from each one. Boom. Notice that if you knew oxygen liked to make 2 bonds, you might actually sit there and go, oh, okay, we're gonna have hydrogen. Ooh, we have oxygen. Probably gonna double bond that because carbon likes 4 and oxygen likes 2. To fulfill the oxide of the oxygen, we need 2 more. 2, 4, 6, 8, 10, 12. That's seeing into the future a little bit. I don't expect you to be there. You can draw that, see if you're over, and then make it your impression from there, right? Obviously, if you need more description on that, here are the step-by-step program for that. Let's do another one. We got NAF. Who's likely to go in the center here?
Nitrogen.
Very good. Honk, right? H-O-N. N likes to make 3. So we get 11 plus 7, which equals 18. nitrogen in the middle, fluorine, oxygen. Can anybody see into the future? What might happen if we get this far? What might we think about?
Double bond with oxygen.
Good, who was that?
Cocoa.
Nice, Coco. It might double bond with oxygen. Let's do it. If you get that feeling, it's probably right. So 2, 4, 6, 8, 10, 12, 14, 16, 18. If we didn't see that, it is still fine because we would have sat there and gone 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I'm 2 over. Well, I know fluorine is a halogen, so it's not likely to double bond. It can't double bond. It never double bonds. So then we would see that there, and then we would go like this. Now for the trickiest question all day. What's the shape of this?
Is it bent?
It is bent. It's a different bent than you might think. If we take a look, remember we say how many bonded atoms it is. It's bonded to 2 atoms and it has 1 unshared pair. So this is actually the bent that has 120 degrees instead of the bent that has 104.5. We have 2 bonded atoms and 1 unshared pair. The arrangement of the electrons is trigonal planar. The shape is bent. Very good. It looks like it's what? If we just look at the picture on the paper, it looks linear, right? We can't think that way. This is definitely gonna, these electrons here are going to force that down. And it's gonna look like that from a side view. All right, and about, I just got I'm in about 5 more minutes and then I'll let you guys use the last 5 minutes for the work. So if we take a look here, we have N2F. Sometimes you do not have an actual center. We know that N's form more bonds than F's for sure. So we want to start by forming the N-N bond. Now, we cannot put all 4 F's on one side because that would not hold the symmetry that we talked about. But if we put 2 F's on one side and 2 F's on another side, then we're good. Now let me ask you this. Does anybody think that the nitrogen will double bond? How many bonds does the nitrogen currently have?
3.
3, and then we said it likes 3. So we're probably not going to double bond that. If we need to, we can in the end to get its octet, but probably not. So we have 10 plus 21. No, 28, right? 7 times, yeah, 28. That's a total of 38. Here we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38. Now, if I only had 36 there, then that nitrogen would have had to double bond. But I had 38, so we were able to get them all there. For tomorrow, I would like for you to do exercise 5 on page 10. And just problem number 2, I believe. Oh, no, sorry, trick jar. Problem number 2 and problem number 4. Problem number 2 on page 13. And problem number 4 on page 14. We're holding off on 3 because we've not learned isomers yet. We'll learn that tomorrow. And we're holding off on 5 because we have not learned ions yet. That's tomorrow. Any questions? If you really want to get the best out of this, you might want to go ahead and put some preliminary shapes down. As I said, we'll probably run through that quickly on a Thursday and Friday, but we'll probably be in the more complex ones by then. So if you have down these little easy ones, then you're going to be a lot better off. That's all I got for today, but let me show you, if you have the time to stick around real quick, let me show you one of the most complex. So if we take a look. Is long or short? I think they're short. Check out this guy. And we may have a student of the month question today. I can't imagine anybody getting this. I will be so amazed. Look at this guy. Oh, I'll put it here. This is what's called an octahedral. First part of the student of the month question. Why does this seem more strange than any of the other ones we've seen? What's a problem with it from what we've taught so far?
It has 6 bonds on it. Like,
And what does that do?
Doesn't it break the octet rule?
Very good. Breaks the octet rule, right? And can anyone tell me, don't look this up, can anyone tell me how it's possible to break the octet rule and have 6 bonds? Ashkar, or what's his name? Actually, it's not in this class, is he? You probably would know this.
I
Doesn't
forget what it's
like
called.
the
carbon do that?
Carbon cannot do it.
Oh.
doesn't like the number of valence electrons increase with different shells. Like the first one's 2,
Who is this?
and then it goes to 8. Coco.
Is it Coco again? You're exactly right, Coco. Very good. Possible student of the month there. If we take a look, remember, we talked about how the S and the P's were being used for the bonding. 2, 4, 6, 8. That's the octet. Think about sulfur or chlorine or bromine. Now you have the possibility 1, 2, 3, 4, 5 of the D's actually coming in. When you have just an octet, we call that sp3 hybridization. It requires an s orbital and 3 p's. This guy right here has sp3 and then d2. So it's actually using 2 of these d orbitals for the bonding. Very good. Yep. And did you base that, just real quick, Coco, did you base that off of your very old ring method?
Yeah.
Yeah, that's a good connection. That's very good. I was wondering, I was thinking like, I wonder how somebody could actually get this, but yeah, if you remember, we have 2, 8, and then some teachers actually taught 18 for that. And that's basically what's happening here. We know that hydrogen breaks the octet rule because it's the first energy level. Everything in the second period has just the 8 octet always. And then if you look, phosphorus, sulfur, chlorine, those guys, they can start to use that third principal energy level because they are in the third period. Very good. That's all I've got for today. Not too many problems, and I don't think that'll take you more than 15 minutes. I'm sorry I went long today. If you do have any questions, by all means, stick around. Otherwise, have a great lunch and a great day.
Mr. Jackson, I have a question about exercise 4.
Yeah.
The NOF structure. You said it had 2 central bonded atoms, but aren't there 3 atoms there?
Give me 1 second. I think that you may have gotten that it has two. This one has 2 central atoms. The two N2F4. Either you could say that there's no real central atom, or there is 2.
I'm talking about the one above it, the
Yep.
NOF.
The nitrogen here is the central atom.
Okay.
Yep. I think
okay.
I think you might have gotten fixed, like heard me say it when I was talking about this one, and somehow attributed it to this one.
Okay. Now that makes sense. Okay. Thank you.
Yeah, thank you. Have a great day.
You too.
Bye.
I don't understand how we got like the shape thing.
Okay.
I'm looking at the chart at the very back of the packet right now.
So the one
So
thing,
when it says, yeah, sorry.
so the key thing for this is that you have to get in your mind bonds versus bonded atoms. So this is actually just 2 atoms bonded to the nitrogen, even though we see 3 bonds there. Notice that we say central bonded atoms. So it's actually the number of atoms, not the number of bonds.
Okay, so number of atoms. So
So 2,
if we had,
2 atoms are bonded here, and we have 1 unshared pair or 1 lone pair. So we go for the first part, we go for how many atoms are bonded. We have 2, and the number of lone pairs is 1.
oh,
That is-
okay, that makes a lot more sense. Thank you.
You're welcome. I know it's always like, we're like, but there are 3 bonds there. Yeah, but there's only 2 atoms bonded to it. And
Okay, thank you very much.
Nice
Have a
job.
good day. Oh, thank you.
Yep. Have a great day.
You too.
Alexa, shuffle my playlist school songs.
Shuffling your playlist. School songs